The idea of this video is to discuss what Lorentz program can do for an application like a penning trap in presence of a residual gas. This is an axisymmetric model in 3D Lorentz program with both electric and magnetic solvers. There are three main things on the screen. One of them are the colored lines, which shows the distribution of the voltages assigned in the system. There is a cylinder with 7,000 voltages attached to it. There is disc magnets at the end attached to something ground and conductive. This is the half of the view right now. You can see full tank and full disc magnets in the translucent rendering. The purple arrows show the magnetic field and its direction generated by the magnets. Magnetic field reach about 2,000 Gauss near the magnets, and then in the region of the interest it is down about 500 Gauss. Here you can see the rays produced by the software in a lot of different colors. Here the path of the electron is also seen. That is a characteristic cycloid type of shape in crossed electric and magnetic fields. Because of the presence of a residual gas, it gets hit by something and goes to a different orbit. So you can see two different cycloid type shapes because of the collision. On looking on the model tree, you can see the physics applied to the model. Under the electric part of the model tree, you can see the setup voltages. When ground and high voltage is clicked, it highlights corresponding model part in orange. Double-clicking on these voltages will open the setup box, and voltages and corresponding volumes can be changed. We are in the trajectory mode of the solver right now, and menu options at the top shows corresponding analysis menu. So the plot of distance versus energy can be drawn along the path of the electron. Clicking on Select All Rays and the Plot button will draw a graph that shows actual collisions taking place. Zooming in on the graph, we can see energy variations as electrons move around. If you right-click, it will show up a menu where you can differentiate energy versus distance. Now, from the Graph Properties box, you can change the scale. Now red lines drop down, shows that where along the path the collision takes place. From the trajectory menu on the model tree, we can set up the geometry places for emitter, reflector, and secondary emissions. There is also residual gas chamber setup. We can give mass, radius, and pressure values to a gas. This model is an axisymmetric model. This means whole thing is a rotation of a simple two-dimensional sketch. Hence, there is no need to use a 3D program for this model. Now you can see the same thing in a 2D Lorentz program. Rays are generated in this model in red color. You can see this in emitter dialog box here. Here we have taken an electron, proton, and a H-. The idea was that if the residual gas H2 is ionized, then a proton and H- will be released. On the ray appearance dialog box, you can give different colors to the rays for different particles. You can see proton and H- going on in the different directions depending upon charge and mass. Electron is oscillating around. You can switch to 3D mode to see it conveniently. The plot of energy versus distance again shows a couple of collisions happening here. Generation of H- and H+ can be studied in a lot of ways. In the solution dialog box, switching to ray number 1, which is electron, shows 516 nanosecond, covers a distance of 1,385 in the cycloid. Ray 2 does 29 steps and travels only 17 millimeters in 57 nanoseconds. Likewise, Ray 3, which is H-, travels 6 millimeters. Depending on mean free path, these likely don't collide with anything given how far the electron had to go before colliding with the residual gas. There are parametric and scripting options also if you want to analyze further.